Today, we're going to pull back the curtain on the very heart of your computer. We're going to demystify its fundamental blueprint, what's called its architecture, to really understand how it goes from just a collection of circuits to, well, a thinking machine. Let's dive in. I mean, it really does feel like magic, doesn't it? You click a mouse, you type on a keyboard, and this whole world of information just appears. But, underneath it all, it's not magic. It's actually a beautifully organized system. So how does it all really work? Okay, so at its core, computer architecture is basically the master plan. It's the set of rules that dictates how all the physical hardware components are organized, how they're all connected, and most importantly, how they talk to each other to get things done. And when we talk about this blueprint, we're really talking about four main players. You've got the CPU, which is definitely the brain of the operation. There's the RAM, which is kind of like a temporary workspace. Then you have the bus, that's the communication system that links everything together. And of course, you've got all the input and output devices you use every single day, like your keyboard and your monitor. So think about it. You've got all these different parts. You've got the brain over here, the workspace over there, a keyboard, a display. How in the world do they talk to each other? I mean, they can't just shout across the motherboard, right? They need a system. And that system is called the bus. Now, we often imagine it as some kind of super fast data highway. But honestly, a better way to think about it is like a shared basket. Every single component, from the CPU to your mouse, puts messages into this one shared basket and takes messages out of it. It's this really simple, unified system for communication. Let's walk through an example. So let's say the CPU wants to know if you've typed anything. First, the CPU places a message into that shared basket, and it's basically shouting, "Hey keyboard, did the user type anything?" Now, here's the cool part. Every single device is constantly peeking into that basket. The keyboard sees its name on the message and goes, "Oh, that's for me," and reads it. Every other device just ignores it. Then, if you did type something, the keyboard writes a response back into the basket, and a little later, the CPU checks the basket and reads that response. And this is why the bus is so clever. Just imagine the alternative for a second. A dedicated wire running from the CPU to the keyboard, another one from the CPU to the mouse, another from the RAM to the hard drive. It would be an absolute impossible mess of connections. The bus keeps it all clean and efficient. Alright, so now we know how all these parts can talk to each other. Let's zoom in on the two most famous parts of any computer. RAM, which is the workspace where all the action happens, and the CPU, the brain that does the actual thinking. So RAM, or random access memory, that's the computer's main memory. The best analogy really is your own physical desk. When you're working on something, you pull out the papers and tools you need, and you put them right there on your desk for easy, fast access. That's exactly what RAM does for the computer. It holds the programs and data that it's actively using right this second. And of course, this desk has gotten a whole lot faster and more efficient over the years. We've come a long way from the early DRAM to the standardized SDRAM that came out in the 90s, and now to the double data rate SDRAM you'll find in most machines today. Each new step basically allowed the CPU to get stuff from its workspace more quickly, which is what makes our computers feel so snappy and responsive. And that brings us to the star of the show, the Central Processing Unit, or CPU. Its job is actually super simple but incredibly profound. Its one entire purpose in life is to execute instructions. That's it. Without the CPU, absolutely nothing happens. Now, if we look inside that brain, there are few key parts. You've got memory registers, which are like these tiny, ridiculously fast little scratch pads for doing quick math. Then there's the ALU, the arithmetic logic unit. That's the actual calculator that crunches the numbers. The instruction register holds the single command the CPU is working on right now. And the instruction pointer, well, this one's really crucial. It always points to the location in RAM of the very next instruction in line. Okay, so we've got all the pieces on the board, a communication system, a workspace, and a brain. But how does it all actually spring to life? What is the fundamental process that makes a computer, well, compute? Because when you strip away all the complexity, all the software, all the different parts, what you find is one simple, incredibly powerful repeating process. And this whole process is orchestrated by a part of the CPU called the control unit. You can think of it as the maestro, the conductor of the entire orchestra, making sure everything happens perfectly in time. And this is the rhythm it conducts. It's called the fetch-execute cycle, and it is beautiful in its simplicity. Step 1. The control unit fetches the next instruction from RAM using the address that's stored in that instruction pointer we just talked about. Step 2. It executes that instruction, telling the ALU to add some numbers or telling some data to move around. And finally, step 3, it updates the instruction pointer so it's ready for the next one, and it repeats. Fetch, execute, repeat. That's the whole game. But here's the mind-blowing part. This isn't happening a few times a second, or even 1,000. This simple cycle repeats billions of times every single second. That unbelievable speed is what creates the illusion of magic we see on our screens. Of course, even the star players need a solid stage to perform on, so let's take a quick look at the system's infrastructure, the supporting cast that connects everything and really manages the flow of all that data. So this table breaks down the traditional support system. You can think of the northbridge as the super high-speed gateway that just connects the CPU and RAM. The southbridge, on the other hand, it manages pretty much everything else. Your USB ports, your hard drives, those I/O slots for things like graphics cards. Now, it's true that modern designs often combine these roles right into the CPU, but this classic structure really shows how all the different data speeds are managed. So there you have it. We started with this high-level blueprint, just a collection of specialized components, and we ended with a simple core cycle that, through sheer blistering speed, brings that entire blueprint to life, performing billions and billions of actions every second. This quote really just sums up the whole dynamic perfectly. It's this perpetual dance between the CPU and RAM. The CPU is caught in this never-ending cycle of reading instructions from RAM and then immediately executing them over and over and over again. Everything you do on a computer, whether you're browsing the web, editing a photo, or exploring new worlds in a game, it's all built on this one simple foundation. The simple cycle, repeated billions of times per second, is the engine of our entire digital world. Which really only leaves one question: what are we going to build with it next?